We're going to go ahead and revisit this problem we saw in the last video on kinematics, and the reason why is because I want to show you that even though we have all those equations, that we don't actually need them to solve problems. And sometimes, maybe not all times, and probably not with this particular example, but sometimes it actually makes sense to use graphs to answer questions and to analyze a situation as opposed to the equations. Okay, so we're gonna go ahead and use graphs to solve this one instead of the equations. Okay, graphs and just our knowledge of the relationships between the quantities. So we're gonna start off with a velocity graph, and if you remember, the missing pieces of information for this problem were acceleration and time. Okay, and so we know that at the beginning of this scenario, we have this car going 27 meters per second. Okay, and it slows to a speed of 22 meters per second after some amount of time. Okay, and so here we have a graph of the velocity of that car. Okay, so from here we can, so we'll say this is 27 meters per second, and this is 22 meters per second. Okay, so we also know that the car has a displacement of 80 meters. Okay, and so to get started, we have to remember what our relationship is with the displacement and velocity. So if we're looking at a velocity graph, how can we find displacement? We do it by finding the area. Okay, so we're going to find the area under this graph. We don't know how much time it is. We're going to call this time t. That's what we're going to solve for. We know that the total area of this shape is 80. So 80 is going to be equal to, and we'll say that this is a trapezoid. So we'll say base 1 of 27 plus base 2 of 22, and we'll use units meters per second, all over 2 times the height of t. And that should give us 80 meters. Okay, so if we work this out, 27, 22, add those together, divide by 2, we should get something like, let's see, 49 divided by 2, so 24.5 meters per second times t. We're going to divide that over and get that t is equal to about 3.27 seconds. Okay, and so that's our time. We found it just using some graphical analysis. And once we have this, then we can go ahead and find the acceleration. Either by using our change of velocity, we could find the slope of this line maybe. Okay, let's go ahead and do that. Let's find the slope. So we know that acceleration is the slope of this line. Okay, so you do rise over run. So we have a rise of about -5 meters per second and a run of about 3.27 seconds. So if we say -5 meters per second over 3.27 seconds, that's going to give us our acceleration. Okay, and so we get about -1.53 meters per second squared. Okay, and so you'll see, I'm pretty sure those are the same answers we got before. And you see we actually arrive at those answers using an entirely different method, and we're getting the same things. And in this approach, you might even say that we did less math here, but it was a lot more thinking in order to get there. And so if you're able to do it this way, it's going to allow you to just kind of understand the situation a little bit more deeply. But it is a little bit harder because it does require you to think a little bit harder about what's going on. So we'll look at another example similar to this, and then we'll wrap up this video. Okay, so we're going to take a look at this other one here. So this one's actually be even simpler to use due to using a graph. So we have a car that's accelerating from rest uniformly over time of 5 seconds for a distance of 120 meters. Okay, and again, I like to start with a velocity graph. Okay, so we have velocity and time. Okay, and this time we're starting from rest and we're accelerating at a constant speed, okay, for 5 seconds. So this is 5 seconds. Okay, we know that our initial velocity is 0. We know the time that has elapsed is 5 seconds. And we know that it's going to travel 120 meters. Okay, so if this is, gosh, that was bad. Alright, if this is like a little track for the car, we've got this super fast car right here. This way will be positive, and it's going to just kind of truck along here, okay, for 120 meters. Okay, so we can find, there's missing values here. We can find acceleration and final velocity. Okay, also while we're doing these, I want to encourage you to also be constructing graphs for like position and acceleration. Okay, so here we're starting from rest, so it's going to start kind of flat and get steeper, so it looks something like this for position. Looks like we have a constant acceleration. Okay, so acceleration looks something like this. Okay, so we're going to find these values, and in order to find acceleration, we'll kind of need to find this final velocity first. Now we could use kinematics equations, solve for acceleration first if we want. But if we're going to use graphs, we're probably going to need to find our final velocity first. And so looking at this graph, remember that using the area beneath this velocity graph, that is equal to displacement. And the displacement in this case is 120 meters. Okay, so we'll say that 120 meters is equal to the area of this shape, which is a triangle, so that'd be 1/2. The base would be the 5 seconds. And then the height would be whatever our final velocity is. Okay, so if we solve this for v, you can see that we divide over the 5, multiply by 2, okay, and we're going to get we're going to get units of meters per second for our velocity. Okay, we'll work this out. So 240 divided by 5 would be 48 meters per second for our final velocity. Okay, and then now that we know that this is 48 meters per second, then we can go ahead and find our acceleration. Okay, how do you think we should find our acceleration using our graph? We could find it by finding the slope. So we rise over run, we go up 48 meters per second. We're going over 5 seconds. Okay, so 48 meters per second in 5 seconds is going to give us acceleration. Okay, and that will be a value of about 9.6 meters per second squared, which is actually quite a bit of acceleration. So, okay, there we go. So anyway, I think that this is actually a really good method using the graphs for finding solutions and for analyzing scenarios. Partly, as I mentioned before, because it requires you to really understand the problem a little bit deeper. But it's kind of one of those things where there's a time where it makes more sense to use equations, and there's a time where you could benefit from using the graphs.